With quite a good understanding of how a cache works, we're going to now go over to the next subject, which is virtual memory. So let's revisit our bare 5-stage pipeline where we've now added cache inside. So we have our program counter. Our program counter spits out a physical address, the real address of where something is stored in the world. It goes into the instruction cache, then over to the decode stage, execute stage, memory stage, which goes to the data cache, and back to write back. So that's kind of our bare 5-stage pipeline that we saw. And here as well, the execute stage goes to memory using a physical address. Now, the instruction cache and the data cache both communicate with a memory controller that checks if our address that we gave it is inside the cache, and if it's not, if we get a miss, it goes to main memory and fetches our missing data. So this leads to three fundamental questions. So first of all, what if we don't have enough memory? Remember, we have 2 to the 32 addresses, or maybe 2 to the 64 addresses or something like that. So maybe we don't have enough main memory over here. The second thing is, how do we allocate memory between multiple processes? Because remember, we wanted our processes to have something like the full 2 to the 32 process. 2 to 32 addresses. What do we do if we want to run multiple processes, and then we're really not going to probably have enough main memory? And the third thing is how do we isolate processes from each other on the one hand, so they don't kind of read stuff they're not supposed to, or write over data that they shouldn't be by pointing to the same address because they were just compiled separately? And how do we share data on the other hand between them? So let's look down at these problems, and the first one being the memory size. So if we take an RV32 processor, it has a 32-bit address space, which means it has 4 gigabytes of memory. So this is kind of our address space, and our program starts, at address 0, and it has a total of 2 to the 32 bytes of address space. And it can access any of these 2 to the 32 bytes. That's what we gave it in the compilation. But what if we don't have 4 gigabytes of memory? We only have 1 gigabyte of physical RAM in this example. So what happens is, address 0 will go to the first byte in our physical RAM, address 1 or 4, or depending on how you count it, we'll go to the next address and so on. And at some point, our program is going to crash because it's going to go to an address. It doesn't exist in our physical RAM. And then we're going to get some sort of this type of a picture on our screen that says we don't have enough memory to complete this operation, probably something even worse than that. And this gets even worse if we have several programs that run simultaneously, and really they'll need much more than this, just 1 gigabyte of RAM that we have over here. So that leads us to a huge problem when we say, The second problem we discussed briefly before was process isolation. So we discussed this thing. We have a memory map where we have our full stack of addresses, and we have different areas, text, static data, the stack, the heap, and so forth. And really each program was compiled assuming that it had the full 2 to the 32 byte address space. But what if we want to run several programs simultaneously? And I just took a screenshot from my computer at some point, and you see that different processes are taking up different parts of the memory, and there are lots of processes. There are 119 background processes without me running a lot on my Windows machine. So each process runs a program that was built according to this whole memory map with the full address space. And that means that different processes are going to map to the same address. The program part of each of these different processes is going to map to this memory space that is called text. So that means that processes are going to overwrite data at the same addresses. And also, different data may be read or written to by another process that isn't supposed to be accessing it. So this is a big problem. A possible solution to these problems is what we call base and bounds. And really, this was an early way to deal with these types of processes and these types of problems in old processors. So we can limit the address space during compilation, so we won't actually give the full 2 to the 32 bytes to each program. And then when we load the program, our operating system will define a base and a bound address where the program's address space will start and end. So how do we do this? We basically have 2 registers that are inside our architecture. One would be called a base register, and one would be called a bound register, or something similar to that. And we'll load the base of our address space and the bound of our address space into these registers. Then when accessing memory, basically, we have a CPU memory access over here. It provides a logical address, not a physical address. And that logical address will be added to the base register, which is basically an offset to the address that we compiled to. And that will provide our physical address with which we'll go and access the memory. And since each process will have a different base register, a base address, then we can non-overlap these types of addresses. In addition, we'll have the bound register, which will say what the maximum address is that we're allowed to access with this process, and therefore we'll take the physical address that comes out and we'll compare it to the bound register. And if we went beyond what our bound was supposed to allow us, then we get a segmentation fault. This type of approach is called segmentation. Okay, and the operating system is what allocates the memory to set the base and the bound addresses. The operating system is the only one that can actually access these base and bound registers and make these decisions, and it's done in something that we call a privilege mode. And in the next lecture about operating systems, we'll discuss privilege modes in much more depth. But segmentation suffers from several problems. The address space of each process has to be predefined and limited, and that's not something that we want. It really makes this, we can't do things in a complete, bubble. We have to do things when we're knowing what exactly we're going to run and so forth. The second thing is that processes cannot share data. They are completely separated from each other because if we go out of bounds, we're going to have that type of a segmentation fault. And one of the biggest problems is that segmentation results in fragmentation. So let's see what fragmentation is. We have our 4 gigabytes of memory space over here, and we have program number 1 that actually was compiled to only use 1 gigabyte of memory, and so the processor provides it the first 1 gigabyte of physical memory and sets the base and bound registers accordingly. The second program comes in, it needs 2 gigabytes of memory, and the operating system allocates it the next 2 gigabytes of memory. The third one comes in, and it wants 1 gigabyte of memory, and great, we have 3 processes that are running in our address space, and everything is good. But then, process number 1 ended, and we go and we disallocate this type of memory, free it up, and so we have this kind of hole in our address space. And so another program comes in, and we want to fit it in there, but it already is too big. It wanted 2 gigabytes of memory, and we can't fit it in. And this gets even worse. We have many programs coming in and many programs finishing, and we get this real mess of segmentation over here. And so what happens is that the OS has to go every once in a while and try to fill in the holes and move around memory space, waste a lot of time, resources, and sometimes also it just doesn't work. Some architectures actually still use segmentation today. x86 supports it, but really it's rarely used. Usually we go to what we're discussing today, which is virtual memory. So let's look at a library book analogy to see kind of the a type of problem and how we would solve it. So an author writes a book and sells it to a library, and the library wants to put the book on the shelf. But does the author himself print the location of the book inside the particular library on the book cover? That would be pretty tough, because then every library in the world would have to be set up exactly the same and have the same location where we would put the book. So what do we do to solve that type of a problem? Because it really doesn't make sense. We provide the book with some sort of identifier. We call it an ISBN in the book world. And then we have a catalog, and we go to the catalog, and the catalog has the name of the book, ordered according to alphabet or author or something like that. And it will say, we'll find out what the identifier is. And on that specific card in that specific library, it will tell us where that book is placed inside our particular library. And this is called indirection. It's the concept used to overcome most of our problems. So really the solution to the problems that we discussed above is called virtual addressing. And it's actually been kind of encapsulated by something that is now known as, a bit in mockery, but it's called the fundamental theory of software engineering, or the FTSE. And it states that all problems in computer science can be solved by another level of indirection. And that's kind of a cool thing that was said by David Wheeler or by Butler Lamson, depending on who you look at. But it's kind of a joke, but it actually makes sense, because a lot of problems in computer science are really solved by indirection. So virtual addressing is one of these solutions. It's an indirection that solves many problems. All programs own a virtual address space of the whole 2 to the 32 bytes or to the 64 bytes, or depending on what our architecture is. The operating system maps every virtual address to a physical address that fits in our physical memory, and we have a memory management unit, or an MMU, that will do this translation or indirection. It will translate the virtual addresses to physical addresses. So if we took our example from before, when we do not have virtual memory, the program address itself is the actual address that we have inside the memory. So we have our 32-bit program space, and we have less than 4 gigabytes of RAM. And so what's going to happen is, as we access our memory, at some point we're going to go out of bounds, and the program is going to crash. What happens with virtual memory is we add this MMU, which is this translation type of a layer, and then we talk about a 32-bit program address space, which are virtual addresses. They go to the MMU, ask for the physical address that relates to this virtual address space, and it does the translation. And it can point to anywhere that we have in the physical address space, and even can go on to something like a disk, which will give us a lot of area to overflow the extra memory that we need. So how does virtual addressing work? Well, we're going to divide our memory into units, and the units are typically called pages. DRAM, or main memory, is typically divided into pages, and often these pages are 4 kilobytes, or 2 to the 12 bits of address space. That's kind of a typical size, and so I'm going to be using it throughout this lecture. The processor then accesses the memory with a virtual address. It does not use typically a physical address. And the virtual address, as we can see here, is divided into, the 32 bits over here are divided into 2 areas. So the first area that we can see over here are those 12 bits that correspond with the size of a page, and they're the offset. So they're talking about which byte we want to access inside one of these pages. And the rest of the bits, in this case, we have another 20 bits left, they're going to be the page number, and they're going to be some virtual number that we're going to be discussing that's going to be mapped into a physical page number in the DRAM. So the MMU is this mapping between these virtual page numbers and the physical pages that we have on the disk. It's a whole unit. It may do a lot of other stuff, but it's going to have this translation table. So the page number that we take, we read it out into the MMU, and the MMU is going to replace it with the base address where the virtual page is stored in memory. In other words, the first byte that starts a page. Then we're going to take this offset and go from that first byte we have and go forward until we get to the actual byte that we're selecting with our address inside those 4 kilobytes we have over there. So the mapping between the virtual and physical pages is called a page table. So the MMU stores a lot of these page tables. So let's discuss what a page table is. Or a page table entry is actually one unit inside the page table. So a page table entry is a mapping between a virtual page number, we may use a VPN to discuss it, and a physical page number, we may call it a PPN. Each of the processes has its own page table. So this is process 1's page table, and we see that process 1 has, VPN 0 to 2 to the 32, and inside the page table we say what the translation is between VPN 0 of process 1. It goes to PPN 3 to the real physical page number 3. Process 2 has its own page table, and as we see here, when we go to VPN 0, but we're in the context of process 2, then the physical page number that it's pointing to is actually physical page number 6. And so therefore we can have the same address basically over here that points to 2 different physical pages, and therefore these 2 processes are not overlapping each other. The page table themselves are stored in main memory because they get quite big. So they're just another area inside the main memory. The base address of the current page table is stored in a special register. We can call it the page table base register. And when we load a process into the context of the CPU, as we'll again see in more like in the next lecture about operating systems, we will load this PTBR, and it will point to the actual base, the VPN 0 of the process that we're using right now. When accessing memory, what we do is here we're going to load a byte into register T0, and it's at this address, and that's a virtual address now. Okay, first we take the virtual page number out of here, we add it to the PTBR, and then that points us to exactly what our the PTBR was the first page over here. The virtual page number is the offset from the PTBR, so it said go forward 2 pages, and we got to VPN number 2. The second DRAM access now is going to take the PPN that it got out of here. It takes the physical page number, and it's going to use that to go and access the page. Then it's going to take the offset from that and go and figure out which byte to actually select. So we need at least 2 DRAM accesses for every load store operation. The first one to get the mapping from virtual page number to physical page number, because we said these page tables are stored in DRAM. The second one is to go and take the physical page number we addressed and access main memory again and take out the particular byte or word or whatever we want to actually access over there. This is known as demand paging. So what happens if we don't have enough RAM? Remember, we had a 1 gigabyte DRAM on an RV32 machine that had a 4 gigabyte address space. Or let's take a worst case where we had 100 processes, such as we saw were running on my computer, but we only have 1 gigabyte of DRAM. We don't have, 400 gigabytes of DRAM, which we would need to run these processes. So we can use the DRAM as a type of a cache. So again, this is another level of indirection. We'll store everything basically on disk. Disk is really big. We can have terabytes of data on our disk, right? Then only when we actually access a certain page, we'll bring the page onto the DRAM. And this is why it's called demand paging. When we demand a page, we go to disk and we bring the disk into main memory into a physical page number over here. So therefore, we have a valid bit in our page table entry that will tell us if the page is actually on disk or it's in the memory. So in this case, we have a 0 in VPN number 1 valid bit, which means that we're actually pointing to a page on disk, and that will be called a DPN, a disk page number. So when we actually access VPN1 over here, we see that the page is invalid, and that means that the page is on disk, and we have to go and fetch it. This is known as a page fault. So the page fault occurs, and then we go over and we bring that page onto the DRAM. However, sometimes, or often, I guess, the DRAM would be full, and therefore we have to decide which of the pages we want to evict from the DRAM and write them back to disk. And that is called to swap it out. So we take out this page and we bring in a different page, so we're swapping between these two pages. And often the disk area that is used for this is called swap. But accessing a disk takes millions of cycles. It's much, much, much slower than accessing main memory, and for sure much slower than accessing our cache. So this is something we really do not want to do. We want to do it as infrequently as possible. And if we're already doing it, it takes so long, we just invoke software, and we don't usually have hardware that's going to go and handle page faults. It really needs the OS to go and take care of all of that. So what happens when we have a page fault? So we got a read valid equals 0 on the page that we were reading, and so we have a page fault. This is considered a hardware exception or a trap, which means that we're going to invoke the operating system. And the operating system basically jumps to what we call a page fault handler. And again, in the next lesson about operating systems, I'm going to be discussing these interrupts and exceptions in depth. This is a system call. It invokes the operating system. The operating system is going to check, is the DRAM full? If so, what we need to do is swap out that page, write it to disk, and in any case, we need to read the page that was missing onto the DRAM. Now we need to update the page table. So the new page is going to store the PPN in the page table, and for the evicted page, we're going to replace the physical page number that was there with the disk page number that it should point to. And finally, we're going to return to the instruction that got the page fault, and we're going to rerun it. So to reduce the cost of page faults, because these are really, really expensive, again, this type of an operation will take millions and millions of cycles, not thousands, millions. What we're going to do is we're going to try to limit the number of page faults we have, and therefore fully associative page placement is really something that can maximize the type of the miss rate that we have, or minimize the hit rate. And therefore we can do that in the operating system. It will cost us a lot, but again, it's nothing compared to the millions of cycles that a page fault costs. We'll do other things, like we'll add an access bit to our PTE, to our page table entry. This is also called a use bit. And that will help us enable things like pseudo LRU type of handling of when we swap things out. Okay, and we can add a dirty bit as well. A dirty bit says that, this page has been written to since we read it. If it wasn't written to, then we don't actually need to write it back to disk, and we can spare a lot of cycles that it would take to write the page back to disk. We can just read something and overwrite it if the page was not dirty. And another thing is that we can never swap out pages of the operating system because we need to use the operating system all the time. And so if we would swap it out, it would just be too expensive to go bring it back in. Plus, we need the operating system to actually handle the page faults. But really, the best thing to do is to buy more memory. And that's why, really, we want to have as much DRAM as we can on our computers, because that will reduce the number of page faults and the amount of swap we need to use. So let's see if virtual memory actually solved our problems. And our first problem was that we didn't have enough memory. And luckily, that problem is solved. So let's take as our example again. We have this RV32 machine with 1 gigabyte of DRAM. So we have a 32-bit type of a virtual address. Okay, and now what we had there was we had 12 bits of offset and 20 bits of page numbers. But the thing is that now we only have 1 gigabyte of DRAM, which is 18 bits. So we'll just use a smaller virtual page, physical page number. So the 20-bit virtual page number will actually map to an 18-bit physical page number. Example number 2 is that we had 100 processes running on this machine. So if we think about it, it means that each process can use about 10 megabytes of memory. It's actually not that, but a few megabytes of memory. That's, you know, a couple thousands of pages per process. And that can be really plenty for, you know, a lot of these small programs that are running. And we can actually distribute the number between processes. We don't have to preset that it's a certain number of maximum pages that we have per process. So that means we actually are able to, you know, use this huge memory space, this 4 gigabytes that most of our processes don't need anything, you know, anywhere close to that, and distribute it among these many different processes running our computer. And this is what is actually going on in our computers today. What if that's not enough? Well, we can go to disk. There we have our terabytes, but it's going to really cost us a lot of cycles to do that. What about our second problem that we discussed? And that was program isolation. Well, luckily this problem is solved as well. So example number 1 is location and independence. Remember that we wanted to compile a program and assume that it had the whole 2 to the 32 byte address space. So how do we deal with that? Well, each process, we said, has a separate page table. As we saw over here, process number 1 has its page table and process number 2 has its page table. And therefore, you know, we can have the same address, VPN 0 over here and VPN 0 over here, point to 2 different physical page numbers. And all we have to do is really swap the page table base register in order to access the different ones. Example number 2 that we said was a problem was protection. How do we protect, you know, the one process from the other so they think they're running their own thing and we won't have, you know, this process accidentally override some variable that this one is using, or read some sort of variable or something like that that it shouldn't know about. So page table mapping really ensures that one process doesn't access the data of each other, and it solves that problem as well. What about the third problem? The third problem was data sharing. So we could, if the operating system wants that, and we'll be discussing that again in the next lecture, map several processes to the same physical page number, and that will enable data sharing. So so VPN 0 could be pointing to, you know, physical page number 0 if we wanted to. But in order to add some other level of, you know, protection over there, we'll add read, write, and execute bits to the page table entry to have access restrictions. So, you know, not every process can write to everything and so forth. Our third problem that we recognized was fragmentation, and luckily that problem is solved as well. So, for example, we have several processes that are running, and they each need a certain amount of memory. But we divided our whole physical memory into 4 kilobyte chunks, and it could be something different than 4 kilobytes. But as I said, 4 kilobytes is kind of a typical number. But we divided it into these different types of chunks, and that's the resolution at which we can distribute pages to each of the processes. The operating system keeps account of what pages are free, and once a process exits, its memory is freed, and we can really do this allocation in any way we want, and we don't cause fragmentation, or at least it is limited to the resolution of this very small page that we have in the end over here. So indirection completely solves this problem of fragmentation.